Good morning, good afternoon, good evening. My name is Sergio Chavez Perez. Today's webinar falls perfectly within the realm of what we can call the dawn of digitalization. Our speakers do not need introduction, but let me just rephrase and update something that Jerry Schuster wrote as editor for the July-August 2005 issue of our leading journal, Geophysics. We are truly proud and honored to present two giants in the exploration geophysics industry, Anders Robinson and Sven Treitel. They will talk about the early development of digital signal processing in the geophysical analysis group at MIT. We believe historians of 20th century science may cast a blind and ignorant eye to many of the wonderful accomplishments of exploration geophysics. But they can't ignore what the Geophysical Analysis Group and MIT did. In our opinion, the pioneering development of digital signal processing is one of the highlights of 20th century science and technology. This webinar will cover the fundamental contributions that can be considered the foundation of what has evolved to today's hot topics of big data, machine learning, and artificial intelligence. Please note that their book, Digital Imaging and Deconvolution, is on sale in the SCG bookmark through tomorrow, Friday, October the 22nd. This book is also being translated to Spanish by volunteer members of the SCG Latin America Regional Advisory Committee. If you would like to help contribute to this translation, please contact Gabriel Helpi or any of us. And now, without further ado, let us welcome Anders Robinson and Sven Treitel.
Hello.
Yes, hi. Just a small reminder that this information is copyrighted and it will be available on SCG channels. So please do not record or copy this presentation. The information belongs to the authors and SCG. And now I will leave you with Mr. Anders.
Hello. This is really telling what Sven and I did, and a lot of other people as well. So it's called the SCG, the MIT Geophysical Analysis Group. And next slide. Let's see. Actually, the Boston Globe, which is the newspaper in Massachusetts, had a big issue magazine called MIT 150, which was the 150th anniversary of MIT. And they published a special section recognizing 150 valuable contributions MIT has made. And actually, the MIT Geophysical Analysis Group came out as number 32 on their list. And with this quotation from them, "Drill, baby, drill. Back in the day, the techniques for finding new oil deposits were simple. If you didn't find anything, move over and repeat." In 1948, MIT researchers were among the first to apply modern scientific analysis to reports of seismic activity, to records of seismic activity, to create a chance above a shot in the dark of hitting pay dirt. Formalized the Geophysical Analysis Group in 1950, the collaboration spurred the digital revolution, oil prospecting. Actually, I had an uncle that invested in some oil wells, and he really summed up what he felt. He said, well, you people at MIT are working on some theoretical thing that'll probably never come to fruition. We are actually drilling, and we're going to drill this oil well. As it turned out, the oil well was a dry hole, so they just went on and drilled another one next to it. And it didn't seem that actually you only had about a 10% chance of hitting a wildcat oil well those days. You have to drill about 10 wells to find one well that's wet. And that didn't seem to bother people because they were happy to find that wet well, oil well. Next slide. Let's see. Professor Robert Schrock, who is the head of the MIT Department of Geology and Geophysics, said that Cecil Green at Texas Instruments stated, we have sharpened our tools about as much as we can. What we need is some new tools. So back then, people were thinking of some new tools. Next slide. What the geophysics analysis developed was a new tool. And existing seismic methods were analog in nature. The characteristic feature of the MIT Geophysical Analysis Group was that they were digital. These digital methods required for the successful use of the accuracy, storage capacity, speed of a large digital computer. And fortunately, MIT had developed a computer which had magnetic core memory at the time. So it was the first real prototype of a modern computer because it had accuracy. But it was very small today. It'd be considered not much of a computer at all. Next slide. And what happened is that if you look back in 1950, the old-time engineers had spent their lives developing elaborate analog equipment, and they could not concede that the same or more could be done by a thing like a digital computer. It was sort of like if you spent your life doing something, and then all of a sudden people say, we have a new way of doing it. And the new way was by manipulating a lot of numbers. They just couldn't believe it could do what an analog machine could do. And even a lot of people at MIT didn't believe it either. And Jay Forrester was the man who developed the whirlwind computer. And at some point, he was just a research person in the electrical engineering department, but they never offered him a professorship in the department. And finally, he had to go to the Sloan Business School at MIT to get his professorship. And also about 1956, they just stopped developing computers at MIT and turned it over to IBM. They felt that the computer had been developed as much as it could. And unfortunately, Forresters are working on things like the chip and other things that would revolutionize computers. And all that was tossed out. And they turned it over to IBM. And actually, Texas Instruments and other private companies went on to develop the computer chip, which really changed computers. And also they discontinued the geophysical analysis group about 1957. And so it seemed that people wanted analog, but it was not a real, even though MIT sort of turned away from digital, it was a analog run Pyrrhic victory that had a Pyrrhic victory, which meant that the toll was so great that it was really like a defeat. So a new generation of scientists started working in about 1960, and digital then became foremost again. But there was a interruption, and that was a mistake. And next slide. Now, the theoretical work of the GAG involved the linkage of the mathematical work of Professor Norbert Weiner with the physical theory of seismic wave propagation. Norbert Weiner was a professor of mathematics, and he did early work in stochastic and noise processes. His contribution relevant to communication and control was the subject of cybernetics, which is formalization of the notion of feedback with implications in engineering, computer science, neuroscience, and organization of systems. In other words, Weiner had the foresight to actually outline what could be done. And he invented the word cybernetics, which he thought would be a new subject, but it turned out the only part of cybernetics was the word cyber that came through. So that's where cyber came from. And he never lived long enough to really see the development of the digital computer as we know it today. Next slide. And now, in the Stephen Simpson was one of the early workers at the Geophysical Analysis Group, and he developed a lot of the programming, and he to put Weiner's work onto the computer. But with this termination of the GAG, he said all the work that on the computer programming went away like vanishing ink, and meant that he saw that we had to get a more universal language. Next slide. Actually, Sven and I, after the Geophysical Analysis Group was disassembled, went our separate ways. But I met Sven again in 1962 at a symposium at Brown University. And Sven felt that it was time to get these methods to oil companies. And so Sven passed the digital ideas on to people at Amico Research and convinced Van Silverman to bring me as a consultant. And that's when our work together after that took place. We had worked together on the Geophysical Analysis Group, but we started up work again. And we actually started, next slide. Yeah, next slide, I already covered that. Sven realized that people rejected digital methodology because they did not understand the mathematics where sequence and numbers could replace a device. And we decided to write a series of paper at an elementary level. In other words, the real trouble was that people could not accept the idea of digital at a very basic level. You had to get back to the basics. And we wrote our original paper, which was rejected at first by geophysics. And but 2 years after that rejection, our paper won the best SEG paper award. It was translated to Spanish, right? The Mexican Society. So in other words, we went back to the very elementary level, and then we wrote this series of papers, which were next slide, which were later published as the Robinson Treitel Reader. Now, Mark Smith was on the geophysical analysis group, and he actually went back. He retired from Texas Instruments to write a book, and 30 years later, the book came out, and you realize that the book was a workmanship in literature, and I think he was more pleased with that than anything else he'd ever done. Next slide. Now, the Robinson Treitel Reader was published by the Seismic Service Corporation, but it was distributed by the SEG. It contained all the papers we had written, which is about almost 20 papers. And the reader went through several editions. In 2005, the SE determined that the 3 books ever published by geophysics, which had the most influence, was Sheriff's Dictionary, a popular textbook by Milton Dobrin, and the Robinson Treitel Reader. And so it's true that Jay Forrest and a lot of other people never received the recognition that they deserved. And yet, after all these years, people don't even realize that it took a lot of work to get the digital methods working. Okay, I think that's it. Next slide. I think that's the last slide. Okay. Sven?
Yes, I'm here.
Okay. It's right, it's 11:20 now, at 10:20 your time.
Thank you. Well, good morning, everybody. Let me just start from where Anders stopped in a way and illustrate with some pictures some of the things that he brought up. Next slide, please. This is a picture that was developed by somebody I don't know, but I realize you can't see it too well because the resolution is poor, but it tries to illustrate how the field of digital geophysics evolved, and the very ambitious beginning. The author of this chart showed that we begin with Pythagoras and end up where we are today, where the branch that is most is closest to where Enders and I come from is labeled the time series branch, but there are other branches that all go back in a way to the work of Pythagoras. The time series branch is interesting because that is where Wiener, who was mentioned by Enders, and Enders himself, and also yours truly, are mentioned several times for various contributions. So the tree illustrates that whatever progress in science there ever is, it always goes back to the work of predecessors. And sometimes in this flood of modern literature that overwhelms us, we forget the origins of where most of the earlier ideas came from. So the next slide, please. These are the basic references that describe the earlier work that Enders and I did, and they're in the form of two books, which some of you may know and others may not, but if you want further detail, those are the two that are worth looking at, and they're both published by the SEG, by the way. Next slide, please. Enders mentioned Professor Norbert Weiner. He was a student of Norbert Weiner's, and I took Norbert Weiner's course, although a better description of it would be that I was taken by Norbert Weiner's course, because when I took the course, I barely understood a word of what he said. And it was only because of my other older and more experienced colleagues at the Geophysical Analysis Group that I eventually understood what this was all about. I certainly didn't learn it directly from Norbert Weiner, which is no criticism of his talents as a teacher. Rather, it describes me as a young student. But the filter that is named after him to this day can be described by an input, a desired output, and an actual output. We realized early on that if you design a filter, you rarely can get the result that you want. So you at best get an approximate result. And so the idea was to approximate a desired output by using the well-recognized and well-known principle of least squares that goes back all the way to the work of Gauss and Legendre. And this filter is now known as the Wiener filter, and it is used to this day in many data processing centers of practice expert that work with seismic exploration data. And I'll show you some of the earliest attempts to use this filter. Next, please. This is a picture that comes from Andrews Robinson's 1954 PhD thesis. You have to realize that before Enders published his dissertation, it was news to many people that you could actually do any kind of filtering on a digital computer rather than using lumped networks consisting of resistors, conductors, and inductors. And so this illustrates the implementation of a Wiener filter to reduce the width of a seismic wavelet. And right there on the top, you can see an input wavelet and a desired output, which is simply a sharper version, of the input. And below that wavelet is a filter designed by the principle of least squares, which ideally the desired output was to compress that input wavelet into a simple spike, but that could not be accomplished. But you see an actual output which approximates to some extent, although is not perfect, the desired output. And we also learned that by delaying the output, you give the Wiener filter a chance to do a better job, which is shown in the lower right display. Next slide, please. This is actually the cover page of Anders Robinson's 1954 PhD dissertation. It's called The Predictive Decomposition of Time Series with Application of Seismic Exploration. And if anybody is interested in the history of geophysics, and I think Anders and I are old enough now to have become ourselves probably museum pieces, but I refer you to this thesis, which was published actually in Geophysics in 1965, if I'm not mistaken, in full length. So you can look at these pictures yourself if you're interested in geophysical archaeology. Next, please. This is a page out of his thesis in which you can see the fundamentals of what ended up called today as a method of predictive deconvolution, which is still used by some companies to this day, although it has been superseded by far more interesting and actually much better quality technology. But back in the 1950s, that was rather novel. And on the top, you see a picture of a synthetic trace. And we're not going to describe this in great detail, but by making use of the autocorrelation functions of this piece of a seismic trace, we were able to design a least squares Wiener filter, which is shown in the third line. And the ideal, which was of course not reached, is to convert the piece of a seismic trace shown in the very top to a series of spikes that would indicate where the reflectivities, where the seismic layers change from, say, limestone to sandstone, or from sandstone to mudstone, or whatever. And this, of course, was not reached perfectly, but as I'll show you shortly, it was achieved approximately. We could do better than with existing techniques at the time. Next slide, please. I mentioned that the filter which is used to this day is called either the Wiener predictive deconvolution filter or the prediction error filter. Without going to much detail, being a short presentation is not the place to enter into a lot of mathematics. Suffice it to say that we end up with a filter F that consists of a leading 1 followed by a number of zeros, the number of which can be determined by knowing the depth of the water in which a marine survey is conducted. And such a filter then allows one to operate on a seismic trace, which is this is the prediction error filter working on the seismic trace to produce an estimate of the reflectivity. This was made to show to be possible by the Geophysical Analysis Group. Next slide, please. Now, one of the problems that bedeviled seismic exploration in the early 50s, with people working in the Persian Gulf had discovered that they could not locate, that they could not interpret the marine seismograms because of what they called singing records, which today are the singing records turn out to be multiply reflected seismic energy. This phenomenon was first recognized by names that may be familiar to you, but this K.E. Berg is not the John Berg that many of us know. This is John's father. Maurice Ewing, everybody's heard of, hopefully, and Frank Press as well. Both are now deceased, and the other one is too. But they discovered that the reverberating seismogram really could be described by a waveguide phenomenon. So they attacked this problem by designing a simple analog bandpass filter. Next slide, please. And here it is. And that's on the left is the bandpass filter they designed, and on the right is what they accomplished. And those of you who are seismic interpreters or have been will realize that these results are not particularly good. If this paper were submitted to geophysics today, it would be rejected on site. So there was a good reason for people in those days to design, to see what if we could do any better. Next slide, please. Here is, first of all, what you see trending diagonally across the screen is a piece of punch tape. Why do I show that? That was the way we input seismic information into the digital computer. So we started with the reverberating piece of seismogram that you see below, so the next slide shows the MIT records for the source is the Magnolia Petroleum Company, August 1951. Is that the one you're showing, Myra?
Yes.
Okay. For everybody, apologies for the interruption. I don't know what happened. You can see by the interruption that computers are as reliable today as they were in the old days. But anyway, this is the data that we had to deal with as students. And some of you much younger than I am should feel happy that the data looks a lot better today than it does then. But at any rate, we had to hand digitize this data. And so we were human analog computers. And this digitization was a very laborious process. But these are examples of reverberating marine seismograms as supplied to us, the students on the MIT Geophysical Analysis Group. And we subjected this data to the method of predictive deconvolution, which I described rather poorly, but in a hurry in the preceding few slides. Next slide. This is a picture of Norbert Weiner, who, as Anders mentioned to you already, did not live to see the fruits of his labor. although he was, of course, quite well known even during his lifetime. Next slide, please. This is a picture of Norbert Weiner's title page of a book that appeared in 1947, but the title was The Extrapolation, Interpolation, and Smoothing of Stationary Time Series. And this was our Bible as students on the geophysical analysis group. And the reason I colored it in yellow here in my display is because the students, myself included, called it the Yellow Peril, because anybody who attempted to read and understand this textbook at first reading considered it to be a rather perilous journey. And you'll see why in the next slide, which is a picture of a page on it that I took from my copy of this book. And you see that it's not bedtime reading, or perhaps it is bedtime reading if you want to fall asleep. Next slide, please. After this brief picture and leaving some time for questions, I conclude with the statement that while the geophysical analysis group at MIT was one of the earliest efforts to use digital computers to process seismic information, is certainly the contributors are numerous, and I think we need to give credit to them. So the last slide, please, is a list of some other early digital signal processing innovators. First of all, let me mention those that are known to many of you. There's Milo Backus, who was actually a schoolmate of both Ender's and mine. We were students at the same time. Milo went to work for the Geophysical Service Company in Dallas, where he developed, in parallel to Ender's and my efforts at Amoco, he developed the earlier, GSI was the first contractor to offer digital data processing to the oil industry. Turi Tanner, probably known to many of you, also made significant early contributions. John Sherwood, who luckily is still with us, although he's only 1 year younger than I am, made significant contributions. And then beyond those, there are a couple of names less well known to geophysicists, is Ernst Gilliman, who was an MIT electrical engineering professor. Excuse me. And he contributed significantly to this work as well. Jerome Wiesner, also at MIT, ended up being the president of MIT through his contributions. And Oppenheim was another MIT professor. Schaefer was Oppenheim's student, and to admit that there were other people than MIT graduates or professors who contributed, there is the very significant work of Professor Sidney Burris, who passed away just a year or two ago. He taught at Rice University. So this is a very quick overview of the geophysical analysis group by, I think, the only two living members of that old group. And it's somewhat miraculous that we're still around to give this presentation. So I'll be happy to answer any questions for both of us, since Anders had to leave for his dental appointment. And sorry for the interruption. I don't know what happened.
Thank you, Sven. Sofia Panuncio will take care of the question and answer section.
Yes. Hello, Sven. Nice to meet
Yeah.
you.
Yes,
With some ACG student members, we prepared some questions for you. So
yes.
I'm going to do the interview. What do you consider were the biggest challenges you had to face when implementing something totally innovative in a context where digital tools were still underdeveloped? Probably there were many people against your ideas or who didn't trust your projects. How did you deal with those moments throughout your career?
Well, there was a lot of resistance to these ideas. First of all, as I mentioned in my presentation, people could not the people who sponsored the Geophysical Analysis Group, which were the major oil and service companies of the day, we had an annual meeting and they sent representatives to listen to our presentations. One of the gentlemen in particular talked to me during the intermission and assured me that what we were doing could be done theoretically, but there was no way that we could simulate a analog filter on a digital computer, because everybody knew that this could only be accomplished with lump networks. This gentleman was an electrical engineer working for then the predecessor of what today is ExxonMobil. And he said that the only way you could filter was with a network consisting of inductors, resistors, and capacitors. And I couldn't understand what he was talking about because I had learned in my courses on circuit analysis that you could perform filtering by convolving the unit impulse response function of a filter with an input. And I couldn't understand what he was talking about. So it was only with chatting with some other grad students that we finally figured out what was bothering him. He couldn't understand that the difference between filtering in the time domain and the frequency domain. So this was a sort of resistance that we had to contend with. It was one of the reasons, by the way, why the Geophysical Analysis Group ended in 1957. It was not just, as Enders mentioned, because the Whirlwind computer was shut down, but we at first, most of the oil companies who sponsored us sent representatives who could not fully understand what we were trying to accomplish. And it was only after I was able to join an oil company and talk to the management at what wasn't even called Amico in those days, convince the people there that these methods were worth investigating. And the same thing was accomplished by Milo Backus at GSI, that this technology took off. And that's all. I guess I answered in too much
Yes,
detail.
thank you, Sven. Regarding the connection between academia and industry, what do you think about the importance of a strong bridge between the academia and industry? Do you consider that the existence of a connection between research and industry is essential to ensure a good industrial development in the future? And do you think that companies and society are aware of the importance of geosciences for industrial development?
Well, following the Geophysical Analysis Group, there were, as you all know, multiple consortia created. Some of them have survived to this day, most notably is the Stanford Exploration Project, first led by John Claerbout and currently by his successor. And there are numerous efforts still in progress. Because of the problems that the oil industry is facing today, unfortunately, the number of consortia is no longer what it was at its heyday, and many of the consortia are hurting, they're losing support. This is not because their contributions are not significant. In fact, they are more important today than they were in the past, because many oil companies have stopped doing long-range research. What some oil companies today call research, in the better days of the industry, were actually what we called applied research, but it wasn't long-range research. And somehow long-range research in exploration geophysics is falling primarily to universities. The contractors are doing some, but not enough. And so we're facing a period of time in which it remains to be seen what will happen. It's certainly crucial that there be interaction between the academic world and the industrial world, but there are serious problems that somehow require attention.
Yes. We have a question in the chat. What career advice would you give to aspiring young geophysicists today?
Yes, that is a very good question. I would advise anybody who wants to get an education in geophysics to always consider alternative employment possibilities. That means that you should prepare yourself to get skills that are marketable in professions other than geophysics. But one that comes to mind, which is already being taken by a number of colleagues that I'm aware of, is that imaging, which is a crucial discipline in exploration geophysics, is by no means limited to processing seismic images, but you can use the same techniques to process medical images, to process geographic images, meteorological images, in fact, images of any kind that require enhancement can be submitted to technologies, many of which have been developed by geophysicists. So a good grounding in computer skills and imaging skills should be considered by anybody entering entering our profession, which I think will survive, but it won't be the same as it is today. So it's important to look ahead and sample courses in other departments so that you can make the change when it becomes necessary.
We have more questions in the chat.
Sure, I have all day, so go ahead.
Thank you. One of the younger MIT students was John Claerbout. Can you talk about your early interactions with him and GIG as a model for SEP?
Yes, John luckily is still with us and still very active. And I first met John when I was already working for the oil industry, and I went back to MIT to find some graduate students who we could hire. By the way, I never succeeded to bring people from MIT to work in Oklahoma. But John impressed me. He was, at the time I met him, a senior undergraduate, but he was already interested in getting doing advanced work in geophysics. And I met him, and he asked very pertinent questions, very profound questions. It was clear to me as an undergraduate that this guy was going to go far. And my prediction error in this case was 0, because he became extremely well-known and fabulously successful contributor to our field. And he's really one of the leading exponents of what I would call the second generation of people working in digital seismic exploration. And there are further generations, of course, who are active, very active today. But John is in this second wave, whereas Anders and I and some of the others that were mentioned were in the first wave. Are there other questions?
Yes, we have more. How you look artificial intelligence or ML in geophysics, especially in seismic imaging?
Could you please repeat that question?
Yes. How you look artificial intelligence or ML in geophysics, especially in seismic imaging?
First of all, I take issue with the term artificial intelligence because how can we talk about intelligence when we don't understand human intelligence? So to me, the term is very misleading, as is the term machine learning, because we don't understand how humans learn, let alone we don't know how dogs learn or cats. To me, there is too much hype at current spread about the subject. I look at these techniques as very sophisticated nonlinear multi-channel regression exercises. We don't understand what we're doing, but we do understand that the systems that go under the name of machine learning or artificial intelligence are actually working. I don't dispute that fact. But now, to answer the question, thus far, the results in machine learning are they're interesting and promising, but I think I would feel a lot better about them if I understood, or somebody could tell me what the weights in these artificial neural networks actually mean. Now, there's been some work more recently, which I like, which actually is called, it goes under the name of physics-controlled machine learning, which means that you design machine learning-based filters, but make sure that they obey the laws of physics. And that makes a lot of sense to me. And the results with these physics-guided artificial neural networks, I think, show much more promise than the ones that are designed without the physics, without the application of known physical techniques as conditioners for these calculations.
Yeah, we have one here. Do you see any current technique in geophysical analysis that might revolutionize the field again? Maybe machine learning, as you were saying.
Yeah, well, machine learning, of course, is just in the beginning of its stages. And I've in the previous question, I've given you my feelings, which of course are my own and not necessarily shared by many others. One thing that's almost impossible to predict is what's going to happen tomorrow, let alone what's going to happen a couple of years from now. But I think a field that could evolve further than it has gone today is full waveform inversion. There are efforts now to combine machine learning methods with full waveform inversion. And I think those are headed in the right direction. The early work is promising, but we're not there yet. And I don't know whether we'll ever get there. What worries me is with all these techniques, that the level of effort in the oil companies and even in the contractors is diminishing as time goes by. And the number of papers that you see in geophysics today, although large, is deceptive, because if things continue the way they are now, we will see less and less original work as the number of consortia at universities diminish.
And what is your favorite book on seismic imaging nowadays?
Well, I certainly won't mention the book that I've co-authored, which does not, by incidentally, do a lot with seismic imaging. My favorite book of seismic imaging is unquestionably the third book by John Claerbout, not the second, the third one, which is excellent, and it's as good today as it was when John published it some 20 or 25 years ago. Of course, there are many others, but you asked me what my favorite is, and that's mine.
I have the last one, I think.
Sure.
You are the co-author of an important book, as well as the co-author of 4 ACG Best Paper Awards. Which of them do you like the most? And which one do you think represents your contribution to the field of exploration geophysics the most?
Could you repeat that question, please?
Yes. You are the co-author of an important book, as well as the co-author of 4 ACG Best Papers Awards.
Yes.
Which of them do you like the most? And which one do you think represents your contribution to the field of exploration geophysics the most?
Well, the book, I think the first book that Andres and I wrote together, there is no book that I wrote by myself, because science is a collaborative effort. And so it really goes back to most creative work in the sciences. You stand on the shoulders of other people that work before you. And so if you ask me which of my books that I contributed to I like most, it's the first one. I shouldn't say that because the one that's being translated by this committee is the second one. They're both equally good, in my opinion, but the first one it contains more of the earlier efforts that were made not only by Enders and myself, but our colleagues on the old geophysical analysis group. So that's the reason for my preference. About the future, I don't really know what to say, except that I hope that this, well, I know that imaging will continue to be looked into in various disciplines as it is today. Whether it will continue in exploration geophysics is another matter. I don't know. Very hard to say. I won't make a prediction because most predictions are wrong anyway.
And we have one more,
Sure.
the last one. What do you recommend to the students of geophysics?
I recommend to the students of geophysics that they take courses in related fields, because in today's environment, you never know how long a profession will, a given sector of a profession will last. You must prepare yourself to jump sideways. And especially too narrow a specialty is dangerous, particularly if you're at the outset of your career. I was lucky, and Enders and I were lucky only because we were born at the right time and managed to ride the large wave in exploration geophysics. But you can't rely on being born at the right time. So you defend yourself by broadening your education while at your university. Take a minor in other fields, as related fields. If you're majoring in geophysics, do minor work in related fields, such as electrical engineering subjects, so that you prepare yourself to jump horizontally if the need arises. I couldn't emphasize that more as a parting thought. Just generalize, don't particularize.
Thank you very much, Sven, for your time and for your answers.
And my apologies for the interruption during the talk.
No problem, Sven. Sergio, do you have any final words before we adjourn?
No,
Yes,
thank you.
It was a real privilege to hear Enders and Sven, and thank you so much for everything. And thank you,
Quite
Sophia and Mayra.
Thank you.
Thank you, everyone.
Bye.
And
Bye, everybody.
thank you, Sven. It was an honor to have
Thank
your
you.
speaking
Thank you.
today. Okay.
Thank you.
Bye,
Bye-bye.
everyone. Have a great day.
Bye.
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 Bye.